This video begins with you doing a calculation, and it's a stoichiometry problem. Okay, stoichiometry is when you use reaction equations to calculate amounts of substances. All right, and this question is asking how many grams of chromium 3 oxide are produced by a complete reaction of 10 grams of ammonium dichromate using the reaction below. So I want you to start doing that. All right, the first thing that you should probably think of is this equation balanced, and turns out it is not. There's actually a 4 needed by the water. Otherwise, it's balanced. All right, and in order to do this calculation, you're going to need to know molar masses of the reactant in question and the product in question. And turns out, once you do that calculation, you'll see you have 252.08 grams per mole for sodium dichromate and 152 grams per mole for chromium 3 oxide. All right, so this is a standard stoichiometry problem. We have to convert grams of the reactant to moles using its molar mass. Okay, then we do that. We use the mole ratio, which is actually 1 to 1. I'm just going to write 1 mole to 1 mole, not write out the compounds themselves. And then you convert the product into grams, because that's what's asked for, by using its molar mass. Whoops, that's grams per 1 mole. Okay. And you would get 6.03 grams of product formed from 10 grams of starting material. Okay, so this actually is a decomposition reaction. This is one reactant, and it falls apart into a bunch of products. And the little delta symbol put here actually means that heat is added to get the reaction initiated. All right, and then it goes and it forms gaseous water, gaseous nitrogen, which means that it's going to sputter because it's making gases. It sputters, it makes noise, and I actually can show you a picture of what it looks like. So here is ammonium dichromate. It's a pretty orange color. It's actually prettier than this looks. And when you get it started with its reaction, it really forms what looks like a volcano almost. It has lots of fire, and it creates, as I said, gases and also chromium 3 oxide, which is this grayish, sort of greenish, fluffy substance. And when you're done, you just have the fluffy substance, except that if you dig through that pile, you will find that there's actually still a little bit of orange reactant left. Okay, it didn't all react. Even though it's a fairly violent reaction, it doesn't all react. Okay, so even though we've calculated how much would be formed from 10 grams, just because we stick 10 grams in a container and light it on fire doesn't mean it's going to all completely go. All right, so we have to think about what reality is. Okay, so in reality, reactions don't always go to completion. Often they, either the reaction may stop at some point, or there may be competing side reactions to form other things. But for whatever reason, reactions often don't go to completion, and that ammonium dichromate is one example. So we calculate what we call a percent yield, how much we actually made compared to what we calculated that we would make. So the actual amount, so percent yield is the actual amount made divided by the theoretical amount, and then turned into a percent by multiplying by 100%. Okay, so the actual amount is actually made. And let's say in this case, what actually was made of product is 4 grams. And the theoretical amount is what you've calculated. You should be able to make if all of it reacts. Okay, so the theoretical amount is the amount calculated. And that assumes that the reaction goes to completion, which it doesn't necessarily. And when we did that in the last page, we got 6.03 grams. I'll scroll back and show you. Okay, we got 6.03 grams of product that we should have from the complete reaction. Okay, but it's not complete. All right, what's going on now? Sorry about this. Okay, so it's not complete. So we can calculate our percent yield. So in this case, the actual amount produced is 4 grams. The theoretical amount we should have been able to make is 6.03 grams. Multiply that by 100%, and you'll get 66.4% yield that was made. All right, let's have you try a calculation of a similar type. When 10 grams of calcium metal reacts with water, 5 grams of calcium hydroxide is produced. Calculate the percent yield. So go ahead and try that. All right, so what do? We start by calculating the theoretical yield. So 10 grams of calcium, and we'll turn it into moles using molar mass of 40.078 grams of calcium per mole of calcium. We'll then use the mole ratio, and this equation is balanced. So the amount of calcium hydroxide is, and this should actually be a 2. Hopefully you caught that. Hopefully you caught that there should be a 2 there. The amount is 1 mole to 1 mole. The mole ratio is 1 to 1. And then you can multiply by the calcium hydroxide, molar mass 74.092 grams per 1 mole. Okay, so if you get 18.5 grams of calcium hydroxide. All right, then that is your theoretical amount, or theoretical yield. So now the percent yield, it says 5 grams was produced. That's the actual amount produced. So our percent yield is going to be the actual 5 grams divided by the theoretical, which is 18.5 grams. Multiply by 100%, and you'll get only 27%. And we have one more sig fig, 27.0% yield. All right, the next topic is limiting reactants. And first I'm going to talk about making sandwiches to illustrate the concept. All right, so I'm going to use this is like a reaction equation for making a sandwich. If you want to make a cheese sandwich, one way, this recipe is going to be 2 slices of bread, 1 slice of cheese, and 3 slices of tomato makes 1 cheese sandwich. Okay, this is this recipe. All right, so let's say that we're making a whole lot of these. We're making a production line of cheese sandwiches to sell. And at some point we have left 10 slices of bread, 6 slices of cheese, and 21 slices of tomato. Now we can go through and for each of those reactants figure out how much product you could make. Okay, if you have 21 and you need 3 for each sandwich, then that means you could make 7 sandwiches according to the tomatoes. The slices of cheese, you need 1 for each, so you could make 6 sandwiches according to the cheese. And if you ask the bread would say, well, I need 2 of me for each sandwich, so I can only make 5. Okay, so how many can you really make? You can really make whatever reactant told you you could make the fewest is going to be telling the truth, because there's not enough to make the other two. So you can make 5 sandwiches. And then the bread is what we would call the limiting reactant. It limits how much we can make. Okay, so that's the concept of limiting reactants, and we're going to apply the same concept to reactions, where we take each of the reactants, calculate how much product you could make if that was the one limiting you, and then see which one's smallest. Okay, so the strategy for limiting reactant problems: convert all reactant amounts to moles, which you do for any kind of stoichiometry problem. Calculate the amount of product that would be formed from complete reaction of each reactant. We just did that for the bread up there, 7, 6, and 5. How much product? Then take the smallest amount of product, that gives you your limiting reactant. All right, we'll do one kind of generic example, and then we'll do a more real example. So our generic example is a reaction where we have substance A and 3 substance B's making 2 C's and 1 D. And just to make the example really easy, I'm going to use molar masses that are round numbers. I'm going to say this one is 20 grams per mole, B is 30, C is 60, and D is 70. These are all grams per mole. So these are molar masses. All right, and then we're going to say that, then we're going to look at this reaction and say, well, if we had a problem where we said something like 10 grams of substance A reacted with excess B, how much C would be formed? That would be a case where they're telling you that A is limiting. Okay, but lots of times you're going to be given instead amounts of A and B, and you have to figure out which one is limiting you. Okay, so we're going to do that kind. We're going to calculate which reactant is limiting, and therefore amount of product that can really be formed. Okay, so let's do this reaction, or this example. 3.5 grams of A and 18 grams of B are allowed to react. How much C can be produced? So first we're going to take A and say, what if that one is limiting? Then we're going to say how much would we get if B was limiting, and see which is smaller. Okay, so for A, reactant A, we take the amount and we convert it to moles by using the 20 grams of A per mole, molar mass given above. Then we use the ratio of the coefficients, 2 C's, 2 moles of C per 1 A, and we get 0.35 moles of C produced according to A. Now, according to B, we'll get a different amount. Okay, we have 18 grams of B, and its molar mass was 30. So 30 grams of B per 1 mole, and its ratio of coefficients to make C is 2 C's for 3 B's. So 2 C's, and remember these are really moles per 3 B's. So we do the multiplication and we get 0.40 moles of C produced from B. Okay, so now we know that this one is smaller, so we know that reactant A will run out first and that it is limiting, and therefore the amount of C we will actually produce is going to be 0.35 moles. All right, we have one more problem for you to work, a limiting reactant problem. I want you to try it first, and then I'll solve it. And the problem is when two liquids, hydrazine N2H4 and dinitrogen tetroxide, are mixed, they have an explosive reaction to form nitrogen gas and water vapor. How many grams of nitrogen gas are formed when 100 grams of hydrazine and 200 grams of dinitrogen tetroxide are mixed? Okay, so this started with a problem where you need to put it from words into a reaction equation and then balance it and then do the limiting reactant problem. Okay, so first step we're going to do is balance, or write and balance. Okay, let's not do that. We'll first write it. Okay, liquids, hydrazine, N2H4, and it is liquid, but I'll leave that off, and dinitrogen tetroxide react, they form nitrogen gas, you should know that's N2, and water vapor. Okay, again, we could put in G and gas for water, and liquids for both of those, but I'm just going to leave them off for simplicity. Then you need to balance it. Okay, when you balance it, you should get 2 hydrazines and 3 nitrogens and 4 waters. Okay, so we did that. Now we're going to do the actual limiting reactant problem. We're going to calculate the amount of nitrogen that would be formed if either of the reactants was the limiting one. Okay, so first we're going to look at hydrazine. There's 100 grams of hydrazine. Convert it to moles. Use molar mass. And you should get 32.046 grams. Then use the ratio, 3 moles of nitrogen for every 2 moles of hydrazine, and finally convert the nitrogen into grams using its molar mass. And you should get 131 grams of nitrogen formed from hydrazine, if that were limiting. Now we'll do the second reactant, dinitrogen tetroxide. There was 200 grams of that. And its molar mass, you need to figure out 1 mole per 92.010 grams. And the mole ratio is 3 to 1 for that one. And finally convert that to grams of nitrogen. Okay, do the math and you get 183 grams of nitrogen from the dinitrogen tetroxide. So 131 is smaller, so that is the one you'll form, and that is the limiting reactant.